After going over this for a little while, I also made way too much content for this class. So we're going to do a little bit of a choose your own adventure today. So there's going to be a couple of like, do you want to get more deep into this topic or this topic about halfway through? So not the worst thing. It's also just because hierarchical RL is at least like hierarchical planning in some form has been used a lot. And that's sort of like the first question we'll discuss today. So like I said, we'll cover some hierarchical RL. I'll give like a really good visual example about how this works. One of the larger limitations, and then like the second half of the class is now trying to replace the chunks of hierarchical planning with like LLMs all over the place or new models, and the better or worse ways to be able to do that. Okay, so this is basically the story where there's been lots of robotic solutions. These are just ones from the recent years of to doing parts of hierarchical planning. So like if we look at like even a couple of like algorithms, many of the companies, they're using some form of hierarchical planning, like even Figure's thing, their Helix or whatever is using two components. Pi 0 isn't yet hierarchical planning. I guess that was supposed to be. Hi Robot is clearly. I just finished reading over some of the Google stuff, and although it was not very clear exactly what they're doing, some components of a hierarchical. So this has been used a lot more than you might actually suspect. And it's also because it's a really popular thing to be able to do because it makes it easier to kind of split apart the planning problem. If there's a really complex task, kind of comes maybe a bit naturally to people to think about, okay, well, it could be separated into a couple of different steps at least, and then those problems can be solved faster. Maybe it just comes from like computer scientists are usually taught to do like binary search and stuff like that. So you just learn to separate problems into chunks of a binary tree, and then you just kind of apply that rule a little bit too often. And it goes back even to a concept called movement or motor primitives, which even from biology, there's kind of like a little bit of a structure where maybe part of what we do is a primitive operation for control. And that kind of translated to a fair bit of work in robotics about making motor primitives, which is just like a function that better describes some sort of movement rather than like just torque control at the end. Okay. And then this will start with today's first challenge. Try to give me an example of some robotics control that is not hierarchical control. It's not a trick question, but I do think it'll be hard to do this. About 99% of things are hierarchical. Mm-hmm. Yes, and even if there's like some policy action given state, that action is position control. Okay, well, that's not actually the command that ends up activating the robot. This still gets translated through some sort of PD controller to then become a torque that is maybe eventually applied. Torque, yeah, is also a bit fuzzy too, because you don't apply torques. When it's a robot, we apply current to how it actually works. So there's also kind of a controller even at the torque level occasionally that'll figure out how to achieve that torque. And that's more of an electrical engineering step. But that can also be important. Uh, like for example, too, we don't talk about it much in this class, but depending of the angle of a joint when it goes to try and like use a certain amount of current, it gets a certain amount of torque. So torque is not uniform and like on any real robotic system. It's usually a bit better when we buy more expensive robots because they're better engineered. But like even for a person, like we walk upright, we don't bend our legs a lot when we're walking. Because if we actually had our knees bent more when we walk, it wears more on our knee joints and we'd get older much faster. So it's kind of this point of Pretty much every single policy or control thing that we've seen is at least what I'd technically call some sort of hierarchy. Something, at least if it's not a learned policy, is going to do a bit of filtering, a little bit of control, even at the end of that command. Someone else probably made it, someone engineered it. Has anyone here tried to like tune PD controllers before for position control? Yeah, it wasn't very fun though, was it? Like trying to figure that out. It's a bit easier for robot arms than it is for legged robots. So it's like not a simple problem either. Um, okay, great. So we're still going to go a little bit higher level than this. Well, we're going to assume we can learn both of these levels. So we're not going to talk as much on the detail about learning a position controller, kind of, depending on what level you think of position. But then also trying to do high level planning as well. Okay. So just keep this in mind. Technically, everything I talk about after this is really 3 levels of hierarchy, but we're going to ignore the bottom level, at least 3. Some of them are 4. All right. So, but there's a bit of a reason. So this is about talking more like motivations for hierarchy. But there's also some additional motivations here because part of the idea for hierarchy is at least if you can break the problem into smaller chunks, then there should be some reusable pieces, something that we can make better use of through this model. We talked for a little bit about doing a lot of model-based reinforcement learning, where at least like conceptually, if you've got a forward model and there's a different task with the new reward function, you can just use that model again and have it generalized to a new reward. And this is nice in theory. We talked a bit about the class where this doesn't always work very well because even the forward model is, an expectation. It was trained over an expectation over some distribution, and now it's going to go somewhere else with a new reward function. But how can we still keep around like that motivation of like, well, now we want to learn maybe not something that's going to generalize to a totally different reward function, but it's at least maybe component wise reusable. So that's another like motivation for being able to do a good hierarchy. We've talked about this a bunch. I mean, we spent the last 2 to 3 lectures, talking about goal conditioned RL, where at least, okay, now it's a policy and you can give it a bunch of different goals. So if some new client or user comes along, gives it a new goal, it should achieve that. So it's kind of can generalize well, hopefully across that goal space in a good form. The challenge is though, so even if we're talking about goal conditioned RL, that policy now takes goals. So if it was like goals to move the arm to specific locations in front of it, and now there's some policy that's basically pi, we'll call it call it action, pi of h, given some goal now and some state. There's actually a whole new problem now. Now there's still some extrinsic reward, extrinsic task. What goals does the low-level policy should be specified to that low-level policy in order for it to be able to complete the actual task? So even though there's goal condition policies, sometimes those policies can't solve all goals. And then there's a new problem of figuring out basically how do we specify a bunch of sub-goals to that policy such that it can hopefully achieve them again. And then this again becomes basically some other RL problem. Figuring out how to do this planning is one way to think of it. Okay, does that make sense? Now we're just gonna like stack planning problems on top of planning problems. The decomposition gets, it's very selective. Usually it's like engineered pretty often. Okay. But so this is only 2-level hierarchy, technically. But as we've talked about, I've used this example a few times in the class, like being able to cook. So here there's going to be at least, what do we got? 5 levels for our hierarchy. And then even this level of the hierarchy has other policies so far. So it's possible, like even in this compositional sense, although we want to make the best use of the compositionality, like not only is there policies in terms of hierarchy, there could be policies that specialize in parts of the state space across the hierarchy. So one analogy I often like to use here to be able to understand this is like just think about the way you write code. If you're doing an okay job writing code, you're going to write functions, you're going to write some routines, you're going to make classes, you're going to start to build a hierarchy of a bunch of different things, and they'll specialize in taking care of different chunks of processing data, taking care of actions, being able to process images. And it's just sort of like emerges naturally as you attempt to like create your code better and better over time. So this is one like additional way to think about the hierarchy. It's one of the ways that tends to capture pretty much all of the problems related to hierarchical RL pretty well. Um, it still reflects a lot of the similar concepts. In fact, we'll kind of return to this way of thinking about this problem a little bit later in the slides as well. Okay, so the challenge though is we'll talk about these two pieces. One is to figure out how to combine them. It's not going to always be just as easy as here's a low-level policy, train an RL policy on top of them. And I'll get to a couple of the examples. Okay. All right. So first branch that I'm going to choose to take myself no matter what. Okay. So this is, well, we're going to get into some of the details of it, be able to train some of these policies with a nice navigation task eventually. Yeah. But does that make sense so far? Everyone likes hierarchical RL. Good gosh. Okay. Avert your eyes. Okay. All right. That actually went surprisingly fast. Hmm. All right. So I'm going to give this example for basically figuring out how to do navigation, but on a humanoid robot. So this is a pretty kind of finicky and complex planning problem. At this point, like the control that is actually available on the specific robot is going to be position control for the actual joints. So in this case, it's some prior work called DeepLoco to figure out how to do this type of organization. It's been around for a while, actually, and I'm going to bet you that sometime this year or next year, someone's going to do the exact same thing with a vision language model, and it's probably going to look worse. But they'll get credit for that, I guess, as some type of paper. Okay, so basically it's this problem. Got this kind of blocky looking humanoid agent. It's got 13, I think, parameters for the action space. And the goal is to be able to get this agent over here. This is like X marks the spot, the actual goal it wants to get to. Okay, so let's think about the details of this problem here. There's kind of like two steps. First one, agent has to choose which of these directions to go. And then after it even chooses one of these, it's still going to take a lot of time. So this agent is going to operate at about 30 hertz. So to get from that point, would be able to control things by like individual joints on the robot. I'm guessing it's going to take like 5 to 10 seconds. So we're talking 3,000 steps, or sorry, 300 steps in order to be able to get to that. So this is like also a pretty long planning a problem. We might run into credit assignment issues. We're definitely going to run into potentially some exploration issues. So for example, if the agent was just controlled from here and like initial policy is just like adding noise to the position control space for the joints, what do you think the initial policy is going to look like the initialized random one? Sorry, like going around in circles? Not quite that good. It ends up looking much more like a rag doll. Like from here, if you just add random noise to the joints for this agent just falls down on its face. It flops around all over the place. And it has to learn starting from that distribution of what just looks like someone having a bad time at a dance party or something like that, or maybe a good time, who knows, from that distribution to like coherent stepping behavior that makes it all the way to the other point, like the target. Seems like a pretty good distance to go in terms of policy space, right? So then if we do this, let's just say it gets to choose one of these paths, and we'll talk a little bit about how to learn that right now. But part of one of the problems where this comes up real early is just like the sheer planning problem for it to be able to get from there to that actual point. It's got many hurdles, starting with that distribution. So like I said, so now each of the joints is basically a torque, more or less, in position space. Um, but then the idea is like split this problem into two steps. So to solve that first step where it's kind of like, can we just train the agent to walk as like a good start? So at least it explores in like the space of taking steps rather than the space of flopping all over the ground. So then we can break this into a hierarchy where this low-level controller here is going to take some goals. This is what's actually going to spit out, things that look like the torques that actually go to the agent. But then there also needs to be some goal space here, some action space now that's going to be like expressed to the higher level controller that'll give it sort of those extra details for planning. So if this low level controller, it's just trained, it's going to get a different reward. This is usually one of the trickier steps in the beginning of making this model. So this high level is still going to get this like high level reward. So this is still the extrinsic reward that comes from the environment. But now this thing down here needs some reward. We have already talked about a bunch of examples in the class, so we can just use some of those where the reward for like a particular goal could be like match some pose for the actual whole robot. So it'll kind of snap between a bunch of particular poses as an option. Or there's a lot of other papers that do things for like learning unsupervised representations in order to get this policy to actually match and rely on some latent vector really well. So there's a lot of work to go into training different types of these models that are the lower level control. And we'll get into the high level control in a minute. This particular example is a bit more weird, where the goal space that's going to be used is not very obvious. It's certainly not what we've talked about in the class. That was basically state minus goal and something like that. Because if we're going to do this navigation problem, the goal space that's actually going to be used is the placement of the feet. So it's kind of like if you beforehand, you can almost think that now on the ground, plan out all the footsteps for where the agent should go. And then train an agent to feel like, given the next two footsteps and basically the direction the agent should face at the end of that step, treat that as the goal space. So here, this is not going to be directly controlled. There's going to be like some other function that takes the state, somehow computes like the footstep positions that are going to be at the end of that state, and then minus that from this goal. And that's a little bit more like how this functions. So you can make the goal space whatever you want. Here we had a pretty good prior. In fact, there's a couple of papers that say like most people don't plan more than two steps in front of them either. So that's where we at least got this particular goal structure from. And then, I don't know, there's been a couple of papers on this, but we used a representation for the pose that was just take the center of motion, compute the locations of all the links and their angular velocity, which is a little bit different than like the rotations and quaternions you sometimes see in Majoko. This, to be honest, probably works better, but you need to do a little bit more thought to compute it. Okay, good so far. All right, so this is a lot of different things going to be done here. So this is what we designed. And then the reward, partly because we didn't want our robot to fall and break and for it to have nice motion, actually became two components. This is basically like the goal, the like phi of S minus G goal over here. This one was make the motion not look terrible, basically. So there's going to be, we had a bit of motion capture that you can either get from like a robot, from a person. A lot of robotics papers already have like some type of model-based controller that generates some robotic looking motion most of the time. So then basically now also condition the policy where part of the reward, try and match the like timing of that mocap clip so that it could hopefully look a little bit more natural. Yeah, so this is just low level. So the high level will just be like the actual reward and the environment. So with some details. I'll get to that on the next slide. There's a couple of different odd details in order to get it to work. Maybe I'll just play this. So this is just, we had a lot of prior information on how to make a good low-level controller. And then here, like this is the policy you end up getting out of this after you train it. The little green dots on the ground are the goals it's trying to follow. So it gets sort of close to some of them after a fair bit of training. And this is just like the value functions plotted up on the top right. Okay. So this is nice. This isn't normally what's done. Like often in machine learning, people will just try to train the model to follow some latent distribution. The motion will look terrible. Most of the robotics friends that I know would be terrified to use that policy on their like $1 million humanoid robot. So I might even suggest including, like some motion here. I'm sure that some of those hierarchical policies made for humanoid robots have a lot of inbuilt priors to make it have smooth human-like motion and not fall over. So, okay, but going back to your question, and now this creates its own MDP, and the high-level controller is going to basically ignore that any of this exists here. It's just going to be now something that takes its own action and operates. And then it's going to have a different reward. So here, the high-level controller, it's going to have its own goal as well, but its goal is an angle and a distance that it wants to be able to travel in the actual environment. It's also going to get basically depth perception, as if it's got a depth meter, so it can detect all the stuff in front of it. And this actual like same pose, the low level received, outputs the goal for the low level. Okay. All right, and now some details about the reward. So the reward can then still be like the position of the agent minus the position of the target. That can be the reward here. There's still an interesting exception for this though. So the low-level policy operates at 30 hertz. And the high-level policy only operates at 2 hertz. So now these things are being controlled at different frequencies. So at least one detail about trying to do this well for hierarchical RL. So the reward for this, like the high-level policy, it is technically this, but the best way to usually do this is it's pose kind of minus the agent minus the target, and then like sample this at the 30 hertz that the low level is doing this, and then either do an average or you're supposed to do a sum over all the rewards that the lower level achieves. So this is basically sum of this, kind of like from 0 to 15, just because the low level controller is going to make 15 steps in the world before it returns control back to the high level controller. And then you need to do something with all those rewards. I really recommend doing this sum. There's many times we didn't do this and it never worked. You can't just like take the reward after 15 steps because it'll sometimes look good, but it'll have done terrible things over that half a second it was running in the simulation. Yeah. Okay. Does that make some more sense? There's a whole bunch of different challenges here. A lot of hierarchical stuff has to deal with frequency control. So even though this hierarchical runs at 2 hertz, so 2 times a second, this policy runs at 30 hertz. It's actually kind of slow. And this policy is going to give position control. So it's actually going to give this now to a PD controller. That PD controller actually runs at 600 hertz. So it's going to compute new torques for the actual robot joints, even in the simulator, 600 times a second. And then if you really love and get into the details for simulation, the actual physics step for the simulator was at about 2000 hertz. So the torques don't change there, but it's like detecting contacts, friction, smoothness, in order to make those stable enough to have like good motion so that like this turned out well and the contacts were always very smooth and it didn't like bounce on the ground or slip or slide, 2000 hertz, give or take. So there's a lot of levels of, I don't know, frequencies of control working here. So there's 4 levels of hierarchy, I'd call it, in this particular environment. But we only learned 2. So this does happen in a lot of robots too. Like even some of the legged robots and stuff that we talked about in the class, they'll get controlled at like 30 to 60 hertz, but they're going to have PD controllers that operate at like 500 to 1000 hertz, given those torques. Okay, makes sense so far. Good. Okay. Ah. Okay. So the next step. So this is the network for the high-level policy. The low-level policy is just like a flat network, like 2 dense layers of, I think, 256, nothing special. And then the only kind of uniquely special chunk about this is the terrain or like images is processed through a convolutional neural network. And then this character is basically the pose. And then this is that goal, like angle and distance to the actual goal. So basically kind of separate the network occasionally into these 2 special parts. And then you can combine them later in the model and then eventually output. This is like the goal for the lower level or the high level action. So, and this can all be trained together as one network. So if you do something like this too, where you've got different types of data, if you've got images for your actual robot at the high level, and then you've got some other pose information or sensor information, you'll probably explore a more unique network design. Okay. The nice part is reinforcement learning is awesome. So in this case, it's just like construct the network, figure out a reward function that's pretty easy. And basically, whenever this agent gets within this little radius of the actual goal, it resets further down the path. And then just using the input from the height map, it can figure out how to not run into walls or fall off the cliffs for this auto-generated path inside of this environment. And you can see the ugly looking red dots are like its vision that it gets to see kind of like shooting out of the eyes of the robot here, more or less. Good. Questions? Yes? No? Yeah, it's more of like a relative goal. It's actually just angle from the current facing direction. I cannot draw on a video, it seems. So it's like angle from current first facing direction if the goal is this way. So theta and just the length of that vector. So really not much. Surprisingly, it does end up picking up on this. And some future versions of this, I actually fed this goal into like multiple layers of this network so it wouldn't ignore it as much. Well, like I would put this goal, I would put it here, I'd also put it there, and then maybe on the last layer as well. So it, I mean, I don't know where this is the best way to work out the mathematics that the model's going to learn. So just give it every option to learn where it wants to pick it up. Yeah. Yeah. Yeah, those will probably all work pretty well. Mm-hmm. Uh, question? Good. Hmm. I never ended up trying that, but that might also work well because we don't really know where the transformations are going to happen here such that it computes usefulness for pose. And I mean, the deep learning rule, well, there's what people think the deep learning rule is, which is just like you can feed in the state and it'll interpret all of it, which is maybe the harder way of doing things. And there's the different version, which is kind of like make copies of the input and insert them into your network in multiple places. And it can figure out like how many convolutions need to be used or something like that. Because maybe even the first layer of convolutions really wasn't necessary because there's not a lot of image processing to be done here. This isn't cat or dog faces. This is just like slightly height map changes, and it's just trying to find, you know, like the river path looking in this image. But Because we borrow a lot of stuff just generally from supervised learning. This was just like the typical convolutional neural network. And don't change that design too much because it should work. After that, you can try and optimize it if you want. Yeah. Other questions? Good. No, the first train the lower level policy. Yeah, leave it fixed. One thing you might notice, or at least I'll draw more attention to. All right, so where are the green dots? Can you even see that back there? Can I make? All right. Anything look odd about the green dots? These are supposed to be the goals that the lower level policy has been trained to follow. Yeah. They're really not in distribution for what the low level policy was trained for, is at least one way to put it. They're all too far away. This last picture is great because I think the one, like the second step, is off the cliff, so it did not follow that at all. I'm not, there's not too much to like tell about this, but just, the high level policy is just doing RL. It's going to feed in whatever goal it can get in order for it to achieve high reward, even if the low level policy wasn't strictly trained that way. So there's no communication, at least in this like work, in order to understand like maybe it should specify goals that the lower level policy has seen before or can achieve. Here it's train a low level policy, stick that essentially in the environment, forget that it really exists, train a high level policy on top of it. Yeah, okay. Trickier than you think. So, because I can show this video. So short form would be we'd sample the goals, such like here's the vector in front of the actual agent, pick something that was an average step distance for one step and then add a little bit of an angle for the next step. So this distribution is actually a little bit of geometry according to first step, and then occasionally throw in a larger turn to one way or the other to get this more used to making sharp turns, which is not what's normally, I mean, on average for some of the stuff you might go see in a machine learning conference, it's just going to be like use a normal distribution or uniform distribution. Here, this was constructed a little bit more carefully. Okay, but one additional detail, just about that too. The harder part is figuring out what to do on the left. So if you're going to sample a footstep goal, at least for our low level controller, you also need to sample a motion capture clip. So now we had to create basically a small machine learned model. It was more like a Gaussian process, so like nothing, but basically over a small library of motion capture clips that take steps at different speeds and different angles, figure out for each, like for some small library of footsteps, what motion capture clips do those correspond to. So basically generate a random 2-footstep plan based on just a little bit of like Gaussian noise and some angles. And then from that, pick a mocap clip that most closely follows those footsteps to get good motion. So it gets a bit complicated further you get into this. Yeah. So you mean like no hierarchical RL? Mm-hmm. So not on this paper, but that's the next paper we'll talk about. So kind of good segue, but first step for that question. Well, one, this can also be used in dynamic environments where there's a bunch of other blocks at least chasing you around. They're not chasing here, but you can basically just use the same system. Instead of it being a height map, it's now like a vector field of like the XY velocities of all the objects around the agent. So that at least helps. I think, yeah, you can also use this to play the world's worst version of soccer. Kind of looks more like golf, but you can get some good interaction. And now the goal here is to get the soccer ball. Reward here is to get to the soccer ball, and even more reward for getting the soccer ball to the target goal. So it's nice once you start making this up, you can kind of design a lot of tasks and environments. Yeah, this would learn this lovely hack that it gets the most reward when the ball and is it's close to the ball and the ball is close to the goal. When the ball touches the goal, more or less, the goal teleports away. So it actually does not want to do that. That's just a short story and how annoying it is to make a reward function to do what you want it to do. But if we added a bonus for it being able to like get the actual goal, then it was just so unstable because it was like when it actually got to the goal and it got a huge bonus, that just looked like variance in the policy gradient. So it made optimization much harder. So making a smooth reward function, its own pile of research. Uh, so think about that carefully when you alter your reward. So then this is the not quite your question, but the one before it. So without hierarchy, like at all, so just train the high level policy to output torques instead of the action. This was the best that we could perform with like days more training than the hierarchical version like that we could train so far. Okay. So hierarchy is really helpful for long-term planning. Um, Deep learning RL, you can just feed in basically whatever sensor input you've got. It should be able to figure out how to solve the task. Yeah, concurrent policy optimization and learning some optimal tasks. Now, I've got another fun paper after this where I actually try to play a full game of soccer with multiple agents playing it. It worked okay. It was really hard to train, but that's something people could maybe get into. But short story for the painful version of that. When you add more and more agents to the simulator, the physics simulator does not like that. And it starts to, the physics in it starts to get worse, even at the same control frequency. So might still need more work on physics simulators. But well, some of the newer ones are much better these days. Okay, so then we can get back to your question here. That was good. Now we've at least gotten to like some of the ugly details for how to implement these. And now we can start to roll out a few of the technical problems and then why we want to at least make constructing a hierarchy easier. Yeah. Hmm. It can't do that quite literally, even if you would want to do that. So because of the way the low-level controller was trained, somehow it's upside down. Okay. In this case, so this was trained on motion capture clips for normal walking speeds. So because the low-level controller was trained that way, it can't get beyond that skill. It can't get anywhere as fast as possible. There might be some sort of like really carefully, like if you train the high level forever, maybe it'll finally might be able to figure out how to coax this low-level controller to walk a bit faster, but it never happened in our work. So you'd have to at least add another component to the goal space. So not just footsteps, but maybe also speed, add a bunch of stuff to the mocap distribution for like different walking, jogging, running speeds, and then maybe it can start to do that as well. Like this can't even stop as another fun thing. So like it was also going around that soccer ball at the end because it doesn't know how to stop. It was never trained to stop or even go backwards, but it can't not walk, shortly put. So this kind of makes it challenging for a bit. So like the low level and how it's trained determines a lot of what the high level can even do. So that's good question because both of these connect really well to kind of like the next problem we'll get into, which is okay, it sounds like it would be better if somehow these could be trained together at the same time. Like conceptually sounds good. We'll talk about why it's really hard. So for one thing, I'm going to talk about one other limitation before we even get to that. So this is just like an example of the control of flow now for like the hierarchy, where some high, try to use this notation throughout this high level policy operates up there, and then some low level policy operates at a higher frequency. So it kind of like the high level policy sort of like gives away control to the low level one for a long time. and just does whatever. So at least one of the problems with this, like theoretical one for now, so no high level, okay, most high level control frameworks can't actually achieve the same optimal policy that a flat, like no hierarchy controller could achieve. Because the high level policy here at the very least is only making decisions like every 15 steps, according to the last piece of paper or the last paper. So because of that, it really can't get like a tight bound on the reward because the low level, at the very least, it's like a short proof, the low level policy has control over all those steps. It can't change its reward. It's not running over that right now. So it just can't really get the same bound on performance. There's an exception or two I'll talk about at the end. But then to get that exception to get optimal policies, it seems that it comes at the cost of any sort of practical performance because it makes optimization much harder. Yeah. Okay. So I think we're at about time. Yeah. Now's a good time for us to take a short break, right? Yeah, because we started at 1:30. Let's take a break until 2:30. Mm-hmm. 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 Is that the exploit reward? No. Make reward. Mm-hmm. Mm-hmm. Well, yeah, basically, okay, so you're not supposed to use any exploration bonus. I should probably just remove. I'll go tell Siddharth to remove that from the code because it seems to be causing confusion. You could probably should just be able to use like DQN agent. I'm not even sure explore exploit agent is useful. Mm-hmm. Mm-hmm. Right, okay. Mm-hmm. Okay. Yeah, send Siddharth a message. I just tell him to remove that just so it confuses people less. Okay. Hmm. I don't know. Also, for better or worse, we kind of like We live in the age of software IEDs that can complete code really well. So partly it's like, okay, it might have been designed such that if they do it this way, it wasn't easy to just use cursor to complete the code in 10 minutes. Yeah, parts of it. Hmm. Mhm. Hmm. Oh, like will I? I'm certainly not using like non-hierarchical stuff on the Unitary robot because it'll break it pretty quickly. We'll see. There are some good simulators for that Unitary already, so you can probably sim to real transfer the standing goal condition stuff. But but the for the Go one, good question. Okay. Shoot myself, so you can use that version instead. I do think there's a slightly newer like group you can buy where it does come with a different arm that I haven't used that arm before, like the Go one plus that arm. Yeah, I don't know what the like. Do you want something with legs? I mean, I've got a bunch of loco bots, which are like mobile bases with arms on them that are pretty easy to use. You can use them for the class or the project or for the summer. Just let me know. Um, those don't have legs, but they're much cheaper. They're pretty easy to use. Those are from Trussen. So if you're kind of familiar with like the Aloha robots, uh, yeah, might be able to get away with that. It just we can chat more later. It depends on what you might want to do with it. So like every robot kind of slightly custom chosen for a specific type of task. So like the humanoids, like I'm installing two kitchens in my lab. They're gonna like make food and stuff like that as part of their task because they're like kind of counter height. They can manipulate some things. They've got hands and touch sensors. The like legged robots are too short. The arms on them are too weak to pick up more than 200 grams. So you're kind of just there's a version that comes with a hand. No, I ordered the expensive versions with hands. Yeah, I'm worried about breaking them because they're delicate, but uh, mhm. Yeah, I mean, there's a lot of stuff to do. That's well, that's part of one of the cheat codes I use for my lab for machine learning research. Is like there's only a very few people that can do a machine learning paper and then include a robot in it. So it's like we don't just do stuff in simulation. So trying to get two of those humanoid robots. Hopefully I can figure that out by next week because I need to spend my money quickly. Usually like research money has like a time limit, and I've been waiting to like as projects come up, I'll buy stuff. But now I have to buy things. So we'll see how that works. It's a problem when you're trying to order really complicated stuff that costs like $100,000. It needs like approval through like 5 levels of the school and a bunch of other stuff. It's not just like ordering stuff off of Amazon. Yeah, they're paid through wire transfers most of the time. I don't even really know how those work. So thank goodness. But you can have a look at the Trosson website for some stuff that's mid-range. I usually have like a minimum bar for like should at least support ROS or something like that, because then we don't have to spend any time thinking about software. A lot of the smaller stuff, like there's a couple of $500 robot dogs, but they don't actually have like a Python API or ROS support. So like even if I buy it, we're going to spend weeks doing that. Yeah, so to be honest, often I buy robots a lot depending on their software support and less on their hardware. Otherwise, we're writing a bunch of software. Okay. But I should get back to the class. We're already like 7 minutes over. As this is still well within the topics of the class. Okay. Well, let's get back talking about a hierarchical RL. So now we can still kind of, sorry guys, put this into the place of being able to do like a walking humanoid. Let me just triple check. Okay, I did turn that back on. Um, but now we're going to get into some of like the maybe more fun things we'd want to be able to train. Um, so there's still the lower level. There's a couple of papers I cited here if you just want to train good lower levels that cover like a good distribution of goals. And then there's the higher level policy, and I'll just use this notation. And then this is just sort of like this is the basic hierarchical RL algorithm. Really, the point is training the high level policy in order for it to be able to optimize the actual rewards. And then the policy that's run in the real world is the low level policy. And then every K or so steps, ask the high level policy for a new goal that the low level policy should reward. There's really not much more to it. It's probably one of the reasons it also gains a lot of use in the community because this is pretty easy to code up. You use a bit more memory for another network, but besides that, nothing too complicated. And there's some other papers here you can look at, which are kind of related if you want some more details on hierarchical RL. Okay. So any questions? Okay. I'll at least point out there's certainly one part I did leave out here. So this is going to receive rewards for every single step. But again, what ends up training for this policy is usually going to be a sum over those rewards from 0 to 15 or something like that is what you actually end up giving to that agent for training basically as if nothing happened. Low level policy is running, collect some sum over rewards, return those to the high level policy. Keep training. Okay, so let's talk about some of the problems. One of these is so the performance that you can actually get of the high level policy depends a lot on the low level policy. So here, this quality is going to depend about the distribution of goals it might eventually expect. So in this case, what I'm really trying to get at is the high level is also going to depend on this too. So even if, high of low is trained over goals in this space, but the rewards that it's going to get that make it the best are actually somewhere over here that it's going to eventually want and be able to train from in some way. It's going to be very unlikely that the policy is going to ever actually get to that space, really depending on how well the low level was trained. There's at least an example. If you want, you can go look at this paper. where instead it's sort of like, train a policy action given some Z, some state and theta. But the point here is like you're trying to train this policy on that Z to cover all of the state space. So they're kind of like purposefully trying to reduce or like really make this low level part as big as possible so that hopefully you don't run into this problem where there's some non-overlap in the state space where they can operate. Unfortunately, this ends up also becoming a little bit of a messy dependency. So here, what the high level can achieve depends on the low level. And then the low level can only do so much, but it might give other goals. They're kind of really intertwined in what can actually be achieved. Sort of like saying, as human beings, we can only do so much. But if I give you like an exoskeleton or something like that, maybe you can do a few more things. But maybe the whole point is, there's going to be kind of this, the models are already trained on some particular distribution. So one thing that can be done is, okay, goal, try to train them together because the low-level policy is trained on some distribution. It was trained through reinforcement learning, so we know it can be trained. There's nothing too special about that. And the high level is going to give out goals in this process. And the hope is that these could be trained basically is using these two different policies. At the same time, you have to do a little bit of finicky bookkeeping in order to make sure that rewards are used for one area and rewards are used for the high level policy and keeping these separate. And okay, this is often called concurrent training for reinforcement learning or hierarchical reinforcement learning. But this is also going to be pretty tricky to get working. So maybe I'll give an example. How many people here have been ice skating before, or at least slipped on the ice sometime during the previous winter? Okay, so it's kind of like now think of it as like ice time. Like time you end up on the ice is now a different policy that you're trying to train at that point. But you've only trained your low level policy for like during the summer when it's lovely outside and you suddenly do this transition. You can here quite literally think of this as like, okay, someone is changing the MDP on you entirely and like the physics and how it behaves. So anytime that low level policy is updated, it's redefining the MDP, but the high level policy is, it's trying to compute its maximization over rewards, expectation over the dynamics of the stuff that's sampled from the future state. So basically anytime that changes, it's a whole new MDP. And it's kind of like most of our bets are off on how well it's going to transfer to that new MDP, depending on how much that low level changes. So it becomes pretty unstable pretty quickly. So we're going to need more than just to do this like in a total model free method. We need something else to help make this more stable. So this is just also like, so that's sort of like the hard part. But we can also talk in a bit detail about like the good parts of why we'd want this to work. Because the other way of doing this, kind of the way in that other paper was like try to train a policy that'll work over any possible Z ever. The challenge with this is it tends to be like overkill, like too much work. Because I don't think like everyone in this room can solve any single low-level task ever that's ever happened in existence. And you probably don't even have the time to even like use those, even if you knew how to do them. So this is there's this kind of duality of like, well, actually, it sounds like if we do this really well, we can even reduce the amount of time we spend training the low-level policy because it doesn't need to cover goals that are not going to be interesting or useful for the high-level policy. So this is where, like I was saying, it's unrealistic to sort of train a policy to solve all goals. So like here, if there's this ant agent, it's got some goal to get up over here. It only maybe needs to be trained over some small distribution to be able to reach, I'll call these sub goals that are like just small changes in actual distribution over time. But part of it is like when the agent starts to get really good, it'll hopefully find a nice navigation path over here. It doesn't really need to explore this area or find these other goals in this space because they're not along the more optimal path to get to the goal. Even in this case, you look at this technically, how should I draw this? I'll be more probabilistic here. So this chunk of goal space, it's not needed. The agent only needs to go up and to the right. It doesn't care about figuring out how to go down and to the left. So like training the policy, the low-level policy in order to be able to accomplish that, not so important. So here, if this is done well, ignores a lot of goals that never need to be trained for. The challenge is, okay, that distribution of goals to train for is going to come from some environmental reward instead to help steer that eventually. Okay. The challenge is, like I said, what happens when basically low level changes? It's an entirely different MDP, just like we were just discussing, where the dynamics actually change. So one way you can think of this, non-stationary MDP training process. So it's just kind of like some of the POMDP stuff we've talked about in the course. It's a little bit worse than that because the dynamics are changing quite a bit compared to most problems. But overall, kind of similar. So there's also the inverse thing that we talked about too. So even when the high level changes, the low level policy was starting to get used to some distribution of goals it was given, and now that's changed as well. So you can kind of obviously see there's a pretty bad like moving target problem for both of them such that they'll never converge. So let's talk about one method to make this more stationary. Okay, so we've got this problem where basically data in the replay buffer is going to become, you can think of this as it becoming off policy. So there was basically some low level policy right now is going to start out at some start state. It's been specified like pi of little a given the goal of a comma s, and it's going to end up getting to b originally when it collected that data in the environment. Now, though, like the policy has been updated, the low level one, and now when it's still given the command to going to A, it's going to end up down here at C instead. So now it's also kind of unfortunate this data can't be used because now all the stuff that's B, that's like the replay buffer is full of B. But actually, if it's asked to do the same goal right now because the dynamics changed, it's going to go to C. Okay. But if we hopefully don't dig too far into our memory and we remember some of the concepts from hindsight experience replay, is there may be a way to relabel this data such that it's like more on policy for what the current low-level policy would achieve. There is a way to be able to do this. It's a bit tricky, but basically just use this idea. So we have access to the low-level policy. We can query it. It's just a deep model. Provide it the current goal that's like pulled from the actual replay buffer. And then basically you can sample around that goal or basically do a short maximization. Like how should this goal be changed such that it'll result in high log likelihood for what is the current policy for this gradient update. So this is literally like the data, this goal is what's being relabeled here. Actually like sequence of goals such that those goals will lead to actions that are now highly likely. So it's a different type of one way of thinking of this. It's like hindsight experience replay. And now at least when the high level policy does its update, it's actually going to do this for a goal that's more likely to be achievable from the current policy. Okay. Did that make any sense? Almost. Okay. So basically we want to relabel these trajectories with a goal that is more likely. So here, what we would want to be able to do is we need to figure out, okay, the policy is it goes to C right now, but we don't have any data of it going from from S to C. We've only got data in the replay buffer from it going from S to B. But we do want to know what it goes to right now. So what we want to do is we basically want to we need to figure out how to change what A is. So actually we're going to relabel A. And what we're going to do is go back and now figure out, what is max to figure out the A such that this is log A given S, something like that. So this will be, maybe I'll do that prime. So basically figure out how to change A here such that the policy ends up getting to C, because that's what it would actually go to from that data that's in the buffer. There's also, I guess, the reverse way of thinking about doing this, like the data that's in the buffer is actually B. And now we need to figure out, okay, what should A be, or what should the goal be in order for it to get to B, which is in the data? It might be C, it's unlikely unless the policy's finished, but go back and figure out, okay, how should A be optimized or changed such that now the actions that lead to it getting to B that are in the data all have high likelihood under that. So we're just kind of like just doing this short optimization here in order to like figure out how to go back, modify this A such that now it's something else, but now it's that particular goal has more likelihood along all the actions that were in those steps. Okay, does that make more sense? Okay. And a lot of the ideas kind of build on top of this. So this is one method that can work. The challenge with this method is that it really doesn't scale well. So if you add like another layer in the hierarchy, now that layer has to do the sampling process for that lower level, and then it has to do its sampling process again for the next level in the hierarchy. So this becomes exponentially bad just to label one tuple in the data set. And you'll have to do this for a whole batch. So this, and most hierarchical RL methods are usually done for like 2 layers. So it's not so bad at the moment. Okay, does that make sense? This is one way to think about overcoming this, at least in this paper called Hero. It's got some nice concepts. Okay, so now is our choose our own adventure time. So we can either talk about share, which is another paper that's much more hierarchical RL. And basically, the general way you can think about hierarchical RL, it's actually just a multi-agent RL problem. There are 2 agents, they're learning, it's pretty unstable. They're interacting on every single step, so it's actually a pretty hard multi-agent RL because usually agents can ignore each other for a while and just do stuff. But you can use that as a way to construct another type of optimization, or we can dive in now to like how to use LLMs to do this. So how many people want to read more about Marl? Gary? Okay. And how many people want to hear more about language models for HRL? No? None? All right, we got 2 or 3. All right, makes sense. Okay, you're welcome to go look at that paper later if you want. So, so there's been like, how does this now graft on to all the recent progress and the many like papers and some companies that are using this? So there've been a number of papers, which I'm going to kind of group together now, calling them all low-level control papers. They're like trying to make a low-level policy. Some of them are a bit fuzzy in this space, but let's just kind of go with that design for now. There's also been a big pile of papers that are like basically using an LLM to generate a plan. So those are kind of like the high-level sounding papers. There's only been a few papers that have tried to put these together in a nice way, and we'll talk about a few of those. So the real challenge here is how to make this combination seamless, just as a term for now, because we're just talking about like we know the benefits of being able to train them together, although none of the papers I'm going to talk about today are them training together because no one's done that successfully, at least from all the papers I could find. But at least trying to take some of the benefits from these, which we didn't talk about a whole lot, but usually there's a lot of design and thought that goes into constructing like the communication space, like that goal description that the low level and high level treat as like the goal space. And that gets a little more fuzzy now when we're starting to use language models. Okay. One thing that could be done, you could use PDDL. All right. Who's familiar with PDDL? Okay. I'm sorry, partly. So the idea is there a text description to describe like a plan? So PDDL is kind of like this logic planning language where you can construct a bunch of things like define a gripper, some predicates and like preconditions on whether or not some actions can be done at certain states. For the purposes of this lecture, let's just say it's a well-structured, basically text or like context. I think it's maybe a context-free grammar such that like you can describe most planning problems with this. There's no ambiguity here. It's just really tedious to write. So this is one way you can now at least ask the LLM, because there's a bunch of other, like PDDL is now 25-ish years old, maybe a bit later than that. And there are many PDDL competitions for figuring out planning problems. So now maybe you can just stick this in the context for your language model, tell it to like find a solution to this plan. That may work. And there's been a couple of papers that have done this. The reason why this might, I'll maybe at least suggest this isn't the most optimal way to do things. It's mostly because it doesn't take great advantage of what an LLM is. An LLM is a natural language kind of compiler in many ways, and not this quite literally looks like another programming language compiler. So it like you need to kind of be an expert in that PDDL language to construct it really well. It also has many, many, many corner cases that you don't want to have to specify by hand. Maybe an LLM will help. But instead, kind of want to go from the other direction. What we'll talk about, like for the rest of the lecture is we really just want to have stats this. Like, I don't want to have to specify a PDDL program. I just want to write, okay, I've got a robot, it's in the kitchen, I want it, or it's somewhere else and I want it to go like fetch me a sandwich or something like that from the kitchen. I do not want to have to write down a PDDL program for it to satisfy this. They're not very human readable either. So I'll ask a bit of a question though, since we're getting into the ugly details. How many people think this will work? Like if you just gave this to an LLM, like just this sentence, kind of two sentences, what kind of output do you think the LLM is going to give? Has anyone tried it before? I can give it a try right here in the class for a minute, but I'm guessing everyone's interacted with LLMs enough. Yeah, so 1 point, probably not providing enough detail or like breaking it down. What are going to be some of the other challenges, even if it does break it down well? Uh, True. So you mean like context for like, it doesn't even know the layout of my apartment or something like that? Yeah. So that's one. So it's not going to break it down. It's not got context. There's still one more that I also is an annoying concept for this as well. Yeah, because it wants to sound really helpful, depending on which version of like ChatGPT you use. But I think that also gets, yeah, to part of one of the last challenges that runs into this too is like, this is just text. Like something, does this, can I just feed this into my robot and it just does those things? I mean, let's ignore all of this stuff for now. But for the most part, it's sort of like, here's a bunch of goals. Somehow those need to like actuate some API that's going to control the robot. So there's going to be like some sort of boundary here. So there's basically these challenges. There's going to be some prompt output, some magic is going to happen, and then somehow the robot is actually going to move. And that magic is going to depend on plan detail. I don't know if everyone remembers that like 6 months where everyone was like, cool, we should all write like API wrappers around ChatGPT and that'll solve all of our problems, and that basically fell apart. And even if the plan is correct. So all of these become challenges when we're using language models as this hierarchy. Okay, so now we're going to go through a couple of papers that like kind of tackle each of these problems a little bit differently. So we can generate plans. We'll start with this one. The plans, they at least need to be achievable, like in the hardware context. So if we just say like, hopefully, robot, please go grab a sandwich from the kitchen, bring it back to me. Um, this is going to have a couple of different problems. One of them that I guess we didn't talk about much just yet is like often the LLM is also going to try and specify a complete plan, which can also be a limitation. Like often like a partial plan is good enough for some average person to be able to satisfy and start acting on. So plan detail is important. So there's a nice paper from a few years ago called Prog Prompt, where basically they're trying to figure out this process using language instructions. They go into some detail. So it kind of takes advantage of two things from the LLM. One, sure, it's good at language, so you can specify the task in a more kind of like natural sense. But one of the parts also is that actually language models are really good at coding. So if this process might happen, basically you can start to add in some conditional information that kind of like looks like some of the code that like literally exists on your robot for like API commands, such that you can still ask some stuff in natural language and it'll output like a short program. It looks very programming. It looks a lot like PDDL, to be honest, but even if you use PDDL as an intermediary, you'd write that. You still need to translate all the PDDL stuff into ROS commands for it to run. This is sort of like, can we just remove all the PDDL step from this? Kind of go pretty close, from the natural language command down to some contexts, some individual tasks that could be described. The hope is like the LLM will fill some of these in and a bunch of different tasks. So this is kind of like just like use the LLM to basically write the program or at least the programming library that would be used to control the robot. So at least it's acting as this glue between even like the high level and low level. And then when it gets more into the details for this, I don't know if any of you do a lot of this type of stuff or have done a lot of prompt engineering, but basically there has to be a bunch of primitives. So you give a lot of the context, like what's in the room, how the rooms are located, the different objects, how fast the robot can go, and then other available objects in there. One example chunk of code that comes from somewhere else, so it can hopefully complete this well enough. And then eventually some actual like task description. And then it generates like the order of operations to come from all this kind of template code on the left. So it does seem to work pretty well overall. And it can generate a plan, a pretty complete plan. It does help though, you still have to rely a fair bit on libraries that are already available. So like language or sort of like some vision model that'll like label stuff in the scene. So like all of this data that comes from over here is like its own machine learning problem to provide the context, but that's sort of skipped so far. Okay. All right. Does that make sense? Questions? Yeah. Is there like a middle moment? Mm-hmm. There's a lot of like mm-hmm. So yes, there's at least one or two papers I know that do like a behavior tree type thing. You send me a message if you want to know those in detail. Okay, but there's actually a slightly better solution. Well, more flexible solution than that as well. That we'll get into on like the next slide. But we'll get there. Question. Uh, that's mostly because they're using an LLM here and like not a VLM. So this paper is not too old. It's from 2 years ago. So by then, like VLMs were not as popular. I mean, even right now, VLMs are pretty hard to use. So if they just want to figure out whether or not it can generate like useful enough planning description language, they can stick in the LLM space. part of this might also be like a familiarity with using LLMs. Like LLMs are not, they don't do everything. You have to kind of get used to like providing things to them such that they end up giving the answer that we want. So like in the way kind of like constructing this, giving it a list so it knows like the options to work over, constructing the output such that it's sort of like you kind of like halfway finish the problem and then just sort of like let it kind of like mumble on and finish the rest of the actual program you're trying to write. So what I'm mostly trying to say is I think like this design for this list is kind of carefully chosen to like work well with like the autoregressive nature of an LLM. It likes lists and just tokens and sequences, and it likes completing lists and sequences of tokens. So I don't know if I can say too much more than that though, about like why specifically this structure, just that I think it comes based off of that nature of LLMs. Okay. All right. So then this gets into the next question that you're kind of getting at. So this is also not a small area of research. The number of papers after just a small search that just like use LLMs to either generate PDL or some sort of planning is growing every day almost. So you can look through some of these other ones if you have some specific questions. I find the text to motion one is actually pretty good if you want to get some more details. But branching off of your question, why not literally have the LLM generate all of the code that's going to control the robot rather than even like a planning description problem? So more than a behavior tree, give the entire Python script that you just like throw right on the actual robot. So this is this piece of work called policies as code or code as policies. At the moment, code as policies. And now this is sort of like give a bunch of the code and sort of the APIs that are available on the robot. And now ask it instead, like not, you know, not the plan for how to get the robot from like the kitchen to yourself, but now like write the Python code that would list out all the commands and actions that would result in the robot getting from the kitchen and to like deliver the sandwich or something to you at that moment. And then just launch that on the actual robot. So I know it sounds a bit crazy. It can work pretty well here, but there's a couple of like mundane details. So one, again, this takes advantage of just the fact that LLMs are also pretty good at coding because they're designed by people that do code, and there's a bunch of good code like text out there to train them on. Yeah, the process will still use like a lot of context about like the code and functions available. In fact, if you go and read the paper, they get down to the point where they're like adding hints into the context about like the functions available in NumPy in order to be able to perform like vector operations. So it can like search out goals and do a bit of math. It also needs a couple of library calls for things like, identify the block or figure out where the banana is next to stuff. So at least one of the challenges of this is there's going to be a couple of lines of code that are essentially like learn an entire perception model. So that sounds a little unreasonable at the moment. But for the moment, like if you add that in the context and we know what perception methods are going to be needed for this, it could just insert those into the code. So this does actually work out pretty well. You're welcome to like go and dig into some of the examples later, because this you can actually just go run on the website and it'll run right there and you can ask queries for the simulator. It's got a pretty good demo. Okay. Does that make more sense? This pretty much. So it's delicate, but it's usually, I put it this way, it's like a great IDE for writing ROS code for be able to control your robot. So, I mean, I would still call that as an advantage. I mean, if we're going to accomplish anything in what we're doing for robot learning, it should just be that it requires us less time to code up policies for robots. And then we can just iterate faster, generalize to things more. So that's like a nice paradigm to go with here. Okay. Um, so I wanted to touch on this concept too, and we'll see how far, if we get through all the slides today, that's no worries. So we talked a lot about like modularity in terms of control. The fact that There's maybe this cooking task, a whole bunch of things could be pieced apart. Truth is, that's only half the story. If things are done really, really well, there should also be modularity in the perception space. So like the fact that in this example, this is from a paper called the Neuromodular Networks paper. It's a nice paper. Highly recommend people read it. But the idea is like maybe perception should also be like a slightly modular concept. The fact that like if you want to translate an object inside of an image, you can just train a network that does translate, or train a network that does like find the red dot in the actual image. So here, this is just like learn to attend on red, and it'll find this chunk that it attends over, and this will attend on circle, and it'll find all the circles in the actual image. And the idea is like, well, now if these models are learned for perception that can also be composed, they become very reusable as well. So then even in the perception problem that's maybe helpful for that programming version of this we just talked about, from there, you can also like do this modularization in the perception space and in the control space. The problem with a lot of hierarchical methods potentially is they only do modularization inside of the control space, missing a lot of like state factorization that can be done in perception as well. So does that make sense? Like, let's just pretend like it's still like a sequence of API calls and some sort of code in order to be able to like detect whether or not a cat, like where it is in an image. Then you could break that apart into at least a couple of like regularly used function calls. The reason why I was saying this is kind of be helpful, there's at least one hierarchical framework called the options framework, which is nice. And this is the one that does actually give like a good theoretical proof for being able to find a proper optimum. But I suspect like options haven't taken off so much. And I suspect it's a lot because of this problem is now they're sharing stuff in the policy space, but they're not sharing network structure for perception very well. So now every specialized agent has to relearn perception, and they might all relearn perception differently. So if they could instead figure out how to share those chunks of perception pieces inside of networks better, then they would probably do their like specialization better. Because this is only supposed to specialize in planning space. But if you learn one model that figures out how to like identify desks, it's probably still useful for all the models that are trying to figure out how to plan in this space. Yeah. Yeah, it most often will. So like in that example, run forward would still be in both of these policies, even though it's technically its own, could be its own thing. So it's hard to figure that out. Shoot, if people are interested too, there's part of the challenge is I think also theoretically like figuring out how to chop apart all these policies is its own NP hard problem, and then also needed to train them. So it's hard to discover this, yeah, like most optimal way to divide the policy space. But then also, yeah, even in action space and in state space, options, at least for most of the papers that I've read, there might be some new ones. And there is a couple of good new ones that do like the option is only the last layer of the network, so they can share a lot of the deep network space. Those ones tend to work even better. So this is also an indicator that if we're making a big hierarchical structure, it needs to be hierarchical in the perception space as well as the control space to get the best, like most out of it. And hopefully you'll understand in the next slide or two why I'm bringing this up, because it ends up being, I think, what some of these are trying to achieve. So this is just a different way of doing hierarchical RL. So options, for what we've talked about so far, just think of them as hierarchical RL. There's a high level or a low level, but the low level can like give up its control to the higher level whenever it wants, really. And just by allowing that sort of like end of its running time right now, allows it to be able to optimize to find a policy as optimal as a flat policy. but it does have this extra point now where it needs to figure out when it wants to give up control, which will often make the optimization more challenging. It's something you often have to do too. Like if for some of these companies that are designing high level, low level control, if they're doing strict hierarchical RL, then like after K step it stops. But there's also like event based planning, like it'll run until like the robot manages to put the stuff in the shelf, and then it knows to query the high level again. So there's different kind of control schemes for different robots. Okay, so we've only got a few minutes left, and we've kind of already covered high robots, so I might go a little faster through this one, and we can go on to the next one. But they're using like a higher level hierarchical method now. Basically, pi zeros on the bottom, and then like a language model version of itself is on top in order to be able to specify plans to the lower level. There's a few details on the way it trains its high level policy. You could probably get into some more of the details of that if you want. But the one I wanted to get to, just because it continues on this story. So Gemini-Robotics also put out a model recently where, at least from the details I can find in the paper, the idea here is they actually kind of do a good version of extending on code as policies. So the idea is like, how do you solve this perception library problem? In this case, rather than having to have now like some model to like perceive an object, maybe another library call for locating it in the image, another library call for identifying it, what should we use instead? That might be the thing where we can like query it for any type of perception problem. Any thoughts? Yeah, pretty multimodal. Yeah, by design. So now it's what it seems to at least be like the advantage of this work is actually itself is also that perception model. So it doesn't need to figure out how to query other stuff, doesn't need to figure out how to write all those libraries. It can ask itself. So it's like, hey, me, figure out where that thing is, and then use that as part of its planning for the actual robot system. So now it's got this robot. It's got still sort of an API, but it's just querying the actual Gemini model to like locate the object in the scene. So if it's sort of like figure out how to grasp like the phone, then the first part will be like locate the phone, and it'll just query Gemini for the phone. It'll point it on location and then like figure out where the phone is or which item is the phone or something like that. And then like now figure out how to plan a path to the actual phone from where the robot arm is. And now where is the hand or something like that. Solving some tasks. It seems to do okay. Most of the report that it's got here is about basically its experiments. There's only like a page or two on how the model is trained and a bit about the data. So you can at least see how it works. I'm mostly saying they're trying to like complete the loop here, and maybe this way of being able to design this such that they're making this like software API for controlling a robot. They're learning the whole API. The way sometimes you can consider this as like instead of ROS, you've got Gemini-Robotics. It's still structured, imposes some structure here for being able to do an API for the robot. And there might be some more details in order to get that to work. But if the goal is to figure out how to make it easier to program robots, then maybe like the data sourced version of doing this, like the data conditioned or data driven way of doing this can work well, or maybe is starting to work well. Okay, does that make sense? We can chat some more after this if you've got some questions, but so there wasn't a whole bunch of details here, but luckily we'll have one of the first authors for the paper present in the class in a few weeks, and you can ask them all the hard details. That's right, I'll message some of the helpers of the organization after this. All right, so then I just want to get to one last caveat, which is VLMs. really, really slow. So if you want to control something that's fast, then at least what they do in this paper is, okay, let's just make one advantage of having that low-level controller. You could train it on a smaller network to solve a smaller distribution of tasks, and it can do it really quick, really energy efficient, and only have to query the VLM, pretty rarely when solving the actual task. And then this, you can have a look at this paper later, basically goes with this design. And I'm actually looking at, it seems to be like a lot of papers kind of popping up like this, like people that want to use VLMs for RL for rewards or policies. You can't because of how slow they are. So you've got to train some small policy, some distilled version of the network in order to be able to run at like fast enough speed to be useful to collect, like 100 million samples we need to do RL. So this is at least one example here. And it seems, yeah, if this is done, you can train much, much faster, get the speed down, get pretty good performance. All right. And then just like a little bit of a summary. So hierarchies, we talked about a lot of things here, but I just want to make it clear like what they're good for, what they're still kind of not perfect for. So you can go look at this paper from Ophir that kind of was like really trying to ask the question of like, what is actually helping? Just well, basically in the hierarchy, we don't want the solution to be, well, it was the expert who engineered the goal space. So like the learning isn't actually helping that much. Fortunately, it doesn't seem to be that. One of the obvious parts where it definitely helps, providing good exploration, providing good, temporally consistent, structured exploration is a big help. Maybe doing a little bit of credit assignment, because now like if rewards are added up and taken at some point, that might provide a little bit more credit assignment than like the agent that might be flopping around all over on the ground. Who knows which one of those random flopping motions resulted in some reward? Hard to tell. The reusability ends up being pretty helpful here, where maybe there'll be a version of a paper soon where now there's going to be a bunch of tasks that come from the high level, and now the low level is going to be trained across kind of like a bunch of high level things giving it commands. So it becomes a pretty reusable low level across many problems. And it's pretty compute efficient. In many cases, there's still a lot of expert knowledge used to like design the programming API for CODA's policies or the goal space for like DeepLoco or Hero. Those always tend to still need to be provided somehow. It's very hard to train these multi-levels together, and we only talked about 2 levels. I only know of one paper that trained 3 levels at a time and didn't diverge. And even that one was tried on some not too difficult tasks. And this last part so high level, even though it seems to be working really well, the split doesn't actually guarantee reaching an optimal policy. Like not the one that's as optimal that could be reached from the low level, or sorry, the flat. Flat means no hierarchy, just one policy controlling everything. Okay. Any last questions? Everyone's excited to use Hierarchical RL for your projects future now? Uh, I've read a chunk of it, but I haven't finished it. That one I didn't think was similar, just because they seem to be still like, well, not still, but like making a good version of a low-level policy that'll control a bunch of robots. And that's still, to be honest, that's often the hard problem, especially if you believe in like Morvig's paradox, where like planning, not so hard. Figuring out how to grasp an object seems to be annoyingly difficult. So like getting that done well is going to make like it really easy for the high level to be able to do stuff. But I don't think they used hierarchy in that paper yet, because they also made like one of the contributions from that work, I think, just because I haven't finished reading it entirely, was like a really fast VLM. That was 2 billion parameters for the low level. So you could like run that probably in like their Isaac simulator real fast. So that makes me think it doesn't have another model that contributes to a hierarchy. But I wouldn't be surprised to see one very soon. But also NVIDIA isn't like one of the companies trying to make a big giant model that can be used as a high level right now. Yeah. And every day I grow a little bit more cautious about reading too many papers from industry because they don't provide as many details as I would like about how things actually work, such that I could go to re-implement them, for example. And I'll, I'm pretty good at implementing stuff. So like if I can't do it, I don't know too many other people would be able to do it. So I'm just, even if I can't do it, then there's like way not enough details in those papers to really know what's going on. It's a bit unfortunate. So I'm probably going to also read less of them, read other papers that have the details in them. So keep them in mind.
I was just thinking about the problem of a hierarchical control where you're learning them at the same time. Have papers listed that you like collect some offline data or like data? Maybe it's not too much, and then the high level policy and low level policy are the data like first, and then once they like converge to something that's quite optimal, then you like put them together, and now they can. I'm thinking like at the start when both policies don't really know what they're doing, and everything's kind of changed off. But maybe you want to just kind of
Yeah.
a little bit of data.
Just like being able to like pre-train any model beforehand, because it might provide a good place to start, such that a lot of optimization problems go away. So I haven't seen too many papers that have done that. It was partly because Hierarchical RL got popular, and then it was too hard to train in this way. But and it's whatever. So like right now, the idea would be the hierarchy is actually like it helps with exploration, maybe. I guess what I'm trying to say is like supposedly with a large enough model and enough data or like pre-trained data, like we saw for StarCraft, things like that, and you train over that, you get over the exploration problem that the hierarchy is supposed to help with. So maybe any single large enough model can embed the hierarchy inside of it. Doesn't need to be specified explicitly, or it at least learns from that data. And I thought that's where the community wanted to go like forever, but now there's a bunch of hierarchical stuff that is coming back in the last year. I suspect though it'll go away. I think it's happening right now just because partly from like Carl's talk, like making a tokenizer that outputs actions properly that generalizes well for a robot doesn't work well, like from a language model. So right now, a lot of this split is happening because it's just too hard to fine tune your average language model to output stuff in like continuous action space that'll work properly and be fast enough. So it's kind of like that's why I kind of put this one as the last paper. Like, I think this problem is one of the motivating splits for when hierarchy is coming back again. Kind of like an engineering problem to be able to control stuff fast enough. Mm. Yeah, I think also what you're getting at is still if the planning problem is chopped up in the right way, like those pieces that are learned can be combined somewhat independently of each other. So like basically if the less specialized policies are also great because they cover a little chunk of the state space, they do it well, and they're easy to learn. So if you like kind of collect a bunch of specialized policies, it should maybe be easier than a big one, but we're kind of going down like a freight train, this plan of just like, no, we'll just learn one big giant model. Maybe implicitly inside of it, it's got a bunch of small policies it's figuring out how to stitch together. And there is a couple of good papers kind of based off your point too, that maybe the point isn't to like learn the hierarchy and train them at the same time, but if you train over enough data, the hierarchy is kind of implicitly inside of that model to activate it. So we'll figure it out at the moment. I like the concept of like it can help with generalization. It's sort of why we started reusability, compositionality. Then you can at least say something about how your model should generalize rather than just we trained it over more data. It probably has a generalization thing in it, right? Uh, I'll just say not many companies or bosses are going to be on board with that plan. They'll be like if you want to do self-driving cars and things like that, you have to start to show mathematically somewhat reliability. It's going to generalize properly, not run people over, things like that. Okay, let's stop there for the weekend. We're already a bit over, but you can ask some more questions, but other people can take off. Otherwise, have a good weekend. I think on Wednesday we're going to have another like group chat in class, and then Friday will either be me or a guest lecture, depending on how much I finish planning for when that person will come give a talk. All right, take care, everybody.